polar form of complex numbers. We have talked about Cartesian, which is x, y, as well as the complex plane, which has the real axis on the x-axis and the imaginary axis on the y-axis. There's another one to look at, and that is called the polar form. And this is where the term our north and south poles come from. We're looking straight down or straight up, depending on your view from space. But I want you to notice here, and that's why I've got it very light. We have a circle, or a series of circles, concentric circles. And we've got both the measures of the radians and the radius. And we're going to use this form to actually measure complex numbers. So the radian is, two radians all the way around the circle. As you can see here, here's 0. There's pi is halfway around. And all the way around, you go to 2 pi, starts all over again. But then the other component here is based on how long the radius is. This is maybe this may be the circumference here. It is circumference, but this is the distance out. And here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can do the radius with this. Looking at this one, we can look at what the radius is as well as the distance around the circle simultaneously. And again, this is called polar form. Now, we use the Pythagorean theorem. And remember, if we're using a circle here, and we already have discussed this several times, if I pretend this is a circle, I'm trying to make a circle here, not doing a good job of it. We've done this before for trig. Where it drops down, remember, this is the cosine going from the angle theta, which is from the origin, and this is my sine here. My x-axis is my cosine. Especially if this is the unit circle, and this is a unit of 1. And then my opposite is my sine. And remember, if this is my a, this is my cosine is the ratio is adjacent over hypotenuse, adjacent of this angle, which is a over r. And then sine is opposite of hypotenuse, and here's theta. Here's the angle, a line opposite theta over r. So sine is b over r. Now, if we multiply each side by r, we're just rearranging this whole thing. And what would I get? If I multiply r here, r on both sides here, that cancels out. I get r cosine theta equals a. And if I put r on both sides here, try to do this, that cancels out r sine theta equals b. Just rearranging. Now, you just want to make a leap of faith with me for a moment here. Let me erase some of this. Sorry, confusing enough as it is, all these squiggles everywhere. So, make a leap of faith here. Instead, we've already done a lot of this. Instead of x and y for a coordinate, as we've done before, and that, remember, is cosine, sine, right? I forgot my s. If this was, as we talked about, if this is the imaginary plane, that's the I, and the real plane, I would write this as the cosine. Let's see. This could be cosine. This would be my real number, which is the x-axis, plus my imaginary number, which is the y-axis. We don't write cosine, sines, complex numbers. We write real plus imaginary. So I could say, basically, what I'm looking at here, this is the called the rectangular form. My z here, if if we call this R, Z, but now we're talking an imaginary complex plane. This is my A, this is my B, but this is imaginary. My Z is going to equal my A plus BI. And I should actually rewrite that as RZ equals, remember, I already did this, the cosine, the radius times the cosine theta, plus the radius times the plus the sine of theta. Instead of cosine squared plus sine squared equals 1, it's r cosine for the real number, that's what the r is, and then r sine times the imaginary number. All we've done here is just rearrange this into complex numbers. Now, express the complex number in polar form. Well, here's 5 plus 2i. And remember, here's my cosine. Here's my sine right here. It's my x and my y. We're just looking at a different way. So, this is basically going to be a plus bi, which is what the standard form is. So my z is going to be r cosine theta plus I sine theta. And let's just plug this in. It's my radius, which is it's an absolute distance. And really, we're just saying we're just finding the Pythagorean theorem. A squared plus b squared equals c squared. Here's a squared plus b squared equals this right here. And I'm going crazy in my pen. Let me erase this again. But really, what we're doing here is, like we did a couple days ago, finding distances and midpoints on the imaginary plane, or I mean complex plane. Well, my 5 squared is 25. My 2 squared is 4. And that's what I've done right here. So a squared plus b squared is c squared. 25 plus 4. So my absolute distance is square root of 29. And that's going to be bigger than 5, less than 6. Square root of 25. 25 is 5. Square root of 36 is 6. So somewhere half there. Now here's where it gets a little interesting. My a is greater than 0. My 5 is greater than 0. So, and tangent is sine over cosine, right? Well, remember, if I said this is x, and this is y, and this is cosine, and this is sine, and we proved last week that tangent equals, man, get away from here, I'm sorry, equals sine over cosine. We already know our sine. Our sine, we said, is 2i. And our cosine is 5. So all I've done here is tangent equals 2/5. And if I do the inverse function of that, it's 0.38. Now, what you got to be careful of is when we do this theta, the angle is actually measured in radians. So all we've done here is 5 plus 2i in polar form is 5.39. That's the square root of 29, 5.39. Is 5.39 times cosine of 0.038, which we figured out here, and sine, I sine 0.038. There's my imaginary coordinate. So another one, rectangular form, 4 plus 3i. Well, 4 squared plus 3 squared, standard Pythagorean theorem here, the 16 plus 9 is 25. So my radius, that distance out from that circle, from the center, is 5. And then what is my polar angle? It's going to be sine over cosine. My sine, remember, is my second one. It's my y here. That's my sine. And then my cosine is my x, or my real coordinate. And that is going to be 3 over 4, because sine over cosine is 3 over 4 here, which is, when I do the inverse tangent, 0.344. So the polar form of 4 plus 3I is 5. It's my radius, going out to circle, which we're going to see in a moment, times cosine 0.644 plus I sine 0.644. Now we can go backwards as well. 13 cosine 0.0707, I sine 0.0707. And by the way, maybe you do remember, maybe you don't. The inverse cosine and inverse sine of 0.77 is 45 degrees. What's my radius? I can tell you this right here. My radius is going to be 13. My real component is going to be 13 with radius times cosine 0.707, which is 9.191. And the sine of 0.77 times 13 is 0.991. So what's the rectangular form? Backwards, my A plus BI is 9.19 plus 9.19. And basically, what we're looking at, the radius is going to be 13. So the real component is, let's see, 7 at the angle 30 degrees. We can overlook this in the regulars. Well, it's going to be 7. Here's another one here, times cosine of 30 degrees and I sine 30 degrees. Cosine of 30 degrees is 0.866. I sine of 30 degrees is 0.5. 7 times 0.866 is 6.062. The imaginary component, the y-axis, the sine, is 7 times 0.5, 0.35. So my rectangular form, and the reason we call it rectangular form is we're basically making a rectangle. Part of the, here's my theta right here. Is going to be my cosine, my sine. Cosine is, for the real component, is the x is 6.062, and my sine is 3.5 times my y component. Now I want to show you the polar coordinate in real use. And like I said, we know how far around it is the circle plus the radius of the circle, because we've been using the unit circle quite a bit. That's unit of 1. What is unit of 5? What is 8? What is the distance 200 miles? Well, this is why I use polar coordinates. So I want to show here, we got a multiply point z. Here's my point z right here. And if we want to go from z to 3z, number one, if you look here, is 1, 2, 3. So it's going to be on this circle right here, or somewhere this z, when I move it from this original point to negative 3i, it's going to be on this third concentric number here. It's on the first one right now, which is 1. And I said there's 2. Here's 4. So it'll be somewhere on this circle, which I was just touching at the bottom right here, too. Somewhere along there. But it's set from 3i. Now, let's see what I does. Remember, I is the imaginary plane. If this is 0, and this is the y-axis, remember, if this was Cartesian coordinates, it should be 1, 0. If it is or the xy, right? And this would be cosine, sine. Well, now we're talking polar coordinates, so it's going to be A plus BI. So this would be 1 plus 0 I. Guess it's just 1 and 0. Now go, and that is, and we go from here to there, it's 90 degrees. That, remember, this is I now right here. This is the imaginary plane plus I, and that is 90 degrees. We've gone from 0 degrees. It's the equivalent. It's like talking radius, except for now we're going from 0, because that's the imaginary plane. If I go from, this is where it gets interesting. Now this is 1, 0. If I go to 0 to negative 1, that goes right over here. And then from negative, I'll underline this here, negative 1 to negative I is another 90 degrees, and negative I to 1 is back to the origin. So a 90-degree turn around 3z would move the same circle around by 90 degrees. So if we're going to do, this is actually, keep in mind, if this is going 90, this original here, it was just going to move, it was just going to move 90 degrees here, or 1i, it would be 90 degrees, because each distance, each from one point to another is 90 degrees, or 1i. So it's right in the middle here. Let me erase all this. I'm making a mess tonight. Sorry about that. So basically, if we're going to move, a little more, okay. If we're going to move 90 degrees or quarter around this circle, now it's polar coordinates, that would go 90 degrees from this point Z would go to there. But we're moving negative I. So we're going halfway around. So if I was going to go halfway around, cursor here, there it is, halfway around 180 degrees, because it's negative. Remember, we're going, if we're moving I, that's 90 degrees, except we're also moving negative. And if we go from 0 to negative I, 0 to negative 1, that'd be 180 degrees right there. And that's the same as negative 1i. We've already moved I, and now we got to move another one. So I kind of skipped to the circle here. But it's not only I, it's not only z of a distance of 1, it's increasing by factor 3. So it's basically 100, it is factor of 3 from 1 to 3, and that's where the 3 comes in. But it's going, since it's negative 1, it's halfway around. And that's, remember, the halfway around is from 0 to negative 1 is right here. That's negative 3z. But remember, I is a 90-degree turn, so we got to make another turn right here. So let's regroup one more time on this. Explain what we're doing. Here's my z. I want to increase it to negative 3i on the polar form. Well, one, it's going to be, like I said, it's going to be, here's z. If I increase it by 3, well, there's 3z. If I go from 0 to negative 1, that's 90, 90, that's 180 degrees. So I've started at z, which had a radius of 1. I increased it by a factor of 3, it's 3z. But then I went from 0 to negative 1, which is 180 degrees. Let's see if I can touch this better right here. Yep. But then it says negative 3i. We've accompanied the 3. We've accompanied the 1 to negative 1, which is 180 degrees, or from the origin to the negative 1. But then there's I, which is another 90 degrees. which goes all the way right there. So it's basically 3/4 the way around, 270 degrees, and it's the radius is increased from a factor of 1 to 3. Let's do one more here. If we multiply the point z on a polar form from -1 minus I, what would the final result be of the new point? We multiply the point z on the polar from -1 to I. So basically, we got to find out the radius of -1 to I. And that's z, multiplied times z, which is, like I said, the radius. Well, remember, this is x, this is y, and this is cosine, and this is sine. And the reason I'm telling you this, we can turn this into a Pythagorean theorem. So, our r squared, our radius, which is the same as our z squared, or c squared, I should say, r squared equals -1 squared plus -I squared, which is basically, when we do this, we put the numbers in. Let's talk about four, they're absolutes. Plus 1 squared, or -1 squared. Well, that is going to be 1 plus 1 equals r squared. Which is another way of saying 2 equals 2. And if r squared equals 2, then r equals the square root of 2. So I'm going to say whatever my original point is at -1 minus I. And by the way, here's the real -1 minus I. It's a 1 minus 1 minus 1. Well, now I got to figure out what that distance is. I've gone my x and y, or say my real and my imaginary. Well, this is the square root of 2. And by the way, it's a 45, 45, 90 because each leg is equal. And it's a right triangle. So this is square root of 2. Well, now I've got to multiply this out. If I multiply this point, my z times 1 minus I, minus 1 minus I. Let's take a look at this here. Square 45-degree angle, quadrant 4. And then, like I said, this is a 45 degree. Multiply it times square root of 2. What we're going to get here is, by the way, square root of 2 is 1.414. And it's going to move it 225 degrees around. Because if I move it halfway around, that's going to bring it right here. Right? And that's at z minus 1. So that is halfway around. And then it'd be minus I, which is 9 degrees around. And it should go right. Another negative I is right over here. So really, I put it right here, but it really should be right there. So it should be not 225. 25. It's the 270. It should be 270, 3/4 of the way around, because I got -1, which is halfway around. And I, well, and it's going backwards because it's negative. Yeah, I is another quarter way around, so it should be right here. It's 3/4 of the way around.